Okay, last time I started to introduce to you one of the greatest experimental physicists in history, Michael Faraday. And we talked about how he was born into a poor family in London, son of a blacksmith, but decided he wanted to be a scientist and managed to get a job in one of the best labs in England. And one of the first famous experiment that Faraday did on electricity and magnetism, I've drawn on the board here. And it looks a little complicated, but let me just explain the basic setup here. He's got two containers filled with mercury. Okay. He has, in one of those containers, he has mounted a fixed magnet, okay, that can't move. So let's just label this one fixed. Now, above that magnet, he has a wire hanging down on some sort of pivot that's free to move. Okay, this diagonal length of wire that I have hanging down into the mercury bath here can move around. Now, that's on one side of his experiment. On the other side, he has a fixed wire dipping into this mercury bath. And here he has a magnet on some sort of pivot that's free to move around, where the north pole of this magnet is free to move. Okay? Now he hooks up a battery and sets the current going. Now he's clearly got a full closed path for this current to go through, right? Because it can go into this mercury bath, be picked up by this wire that's dipping into the mercury, go all the way around, go into the other mercury bath, and back to the battery. So he's got a closed path for the electric current to travel through. Now, when he connects his battery, what's going to happen? That's the question. Something kind of interesting is going to happen. Neat.
The unfixed things are going to spin around the fixed things.
Yeah, that's exactly what happens. Now, why? Okay, now let's think about where the current's going and try to figure out what the forces are. Where is the current going on this wire that's hanging down into the mercury bath on the right here? What direction is that going? And yeah, it's going in this direction, right? Now, what's the force on that hanging wire? Well, it's due to this magnet, right? And the magnetic force here is going out from this north pole, right? So it's going to be going, across the magnet. It's going out, so it's going to be going across the wire in the direction I've drawn. Now, so how do we figure out the force? We take our fingers, point them in the direction of the current, right? Cross it into the magnetic field, the magnetic force, and it's going to actually push this wire out of the board, right? Now, as the wire moves, of course, the direction of that force will change. It will be pushed around and around this magnet. Okay, and as I've drawn it, in the counterclockwise direction. Now, what's going to happen on the other side? We have current now going down into the mercury bath. So what's the right-hand rule for figuring out the direction of the magnetic force, Nick?
Put your thumb in the direction of the current.
Right, so put your thumb down and
Magnet should
your
spin.
fingers should wrap around in the direction of the magnetic force. So this north pole of this pivoting magnet is actually going to go into the board here, right? Does everybody see that? So it's actually going to spin around clockwise. So now, Selah.
Is that sort of like how they invented the clock, or is that
How they invented what?
the clock, or is it different?
Oh, what, electric clocks? No, this isn't so much how they invented electric clocks as it is the first step toward inventing electric motors. Because look what's happening here. As long as he has this battery hooked up, these things just keep moving. I mean, he's managed to produce continuous motion from an electric current. And this was the first time anybody had ever done this. And I mean, notice one of the things that's so striking about this experiment. I mean, there's a couple of things. First, just the one I just said, which was from an electric current, you can actually produce continuous rotary motion here, which people would later make great use out of. But the other thing is that this is a beautiful illustration of what struck people as kind of a strange feature of electricity and magnetism. That, remember, all the forces that we've talked about up till now have just been attractive or repulsive forces. The gravitational force between two masses, just draws the masses together, right? It doesn't make them rotate. Now, the same thing with electrostatic forces. They're just an electrostatic force between two bodies just either either is an attractive force where the bodies, the force on the bodies is directly toward each other or directly away from each other if it's a repulsive force. But here we've got a force that is circular in nature. I mean, we've seen this with Ampere's right-hand rules already, that you point your thumb in the direction of the current and the magnetic force goes in circles around the current. But Faraday has come up with a particularly eloquent way of illustrating that, so you can watch it. You can just watch this north pole of this magnet pivot around and go around in circles around this current. And the same thing with the wire on the other side around the fixed magnet. So you can see his genius as an experimentalist to set something like this up, and so you can just watch these circular forces in action, and from an electric current produce this sort of rotary motion. This was in 1822, I believe. Okay. Does everybody get that? All right, now let's take this a step further now. Since the issue of the electric motor came up, let me give you another setup that will explain to you exactly how you could actually, at least in a simplified form, make a motor out of exactly this kind of effect. So you can call this experiment, let me see, Faraday's rotation experiment. So mark that down in your.
Wait, so instead of first experiment, or?
Yeah, I just didn't want to give it away, so I called it first experiment. I wanted you to see if you could. I wanted you to tell me that those movable parts would rotate. But that's what that's called, is Faraday's rotation experiment. Now let's look at a simple as possible electric motor. Let's say let me see, how do I, okay, going to have to try for one of these perspective drawings. That is horrible. All right, so we have some magnet, and here's the North Pole and the South Pole, and we're going to put a rectangular wire in this magnet, in the space between this North Pole and South Pole, and in such a way well, let me since I'm no good at this drawing, let me give you a side view of how this thing is arranged. Okay, something like that. Now, and then out from the board, we have leads. So there's a current, say, coming in, going in this direction into the board, up top, and out of the board down here at the bottom near the south pole of my magnet. Now, what is going to happen when I hook this up to a battery and start it? What's going to happen? Well, okay, we've got this top wire that's on this side of the magnet. Okay, it's going into the board. The magnetic field, the force, is going down here. The force is going to kick the wire up here in this direction. Okay. I know my drawing isn't very good, but if you have this rectangular loop of wire and the current is going into the board up top here, and the magnetic force is pointing down as I've drawn it, then you take your fingers in the direction of this current up here, curl them down in the direction of the magnetic force, and it kicks the wire to my left. Okay, now, on the bottom, magnetic force is still going down, but the current down here is coming out of the board. It's going to kick it to the right. Right? So the force on this wire down here is going to kick that bottom section of the wire off to the right. So what's going to happen to this whole rectangular loop that I've got? Spin around. Right, it's going to cause it to rotate, right? Why is that? Because you've got this fixed rectangle. The force on the top end of it is in this direction. The force on the bottom end of it is in the other direction. Okay, so there's a torque force on this whole rectangle. It's going to start it spinning.
Oh, so
Yeah, Drew.
like, whatever that is, what is that? Like,
It's just a rectangle of wire that I've placed between the poles of this big horseshoe magnet that I've got. I mean, my magnet, can.
and then that bar that shows that it's coming out, and the two wires that are coming out, is that actually going that way, or is it coming out?
Oh, it's coming. I've got it. I've tried to draw it so it's coming. Think of it as coming out of the board. I mean, I could. You've got a better drawing. But yeah, I mean, you could.
Draw the left wire vertical, and then the top and bottom at an angle.
The left wire.
The one furthest in, you draw it vertical.
like this.
Yeah, and then the top wire at an angle down. It's coming out.
Down. Oh, I see.
So you have to make that lower.
Okay.
No, the other direction.
I have no idea what you're talking about, so I'm not even going to try. Here we go. The current is going in on this side, out on that side. I'm going to give you a side view of this rectangle. Okay, so this is basically what you've got. And so the force on this guy is going to be, it's going to kick him in this direction. Simply because this is the magnetic force going down. So this is the force on the wire, right? Okay, and similarly down here, the force is in the other direction. So you can cause this rectangular loop of wire to rotate just by putting it in a magnetic field and turning on the current. Okay, so if you have a crank, hooked up to this thing, it'll turn a crank. If you had big enough current, a big enough magnet, and you hooked this thing up to a crank that was connected to a bucket of water at the bottom of a well, you could raise that bucket of water up. So this is a way of taking electric current and making it do work for you, making it turn a crank. And people saw this, right away. After Ampere made his discoveries and Faraday illustrated how you could get continuous rotary motion from an electric current, people immediately saw, oh wow, we could make an electric motor. Now, let me see. So does everybody get that much? Okay. Now, there is just in passing, I'll mention that there is something a little tricky here with the battery leads. If you really want this thing to always spin in the same direction, which you would if you wanted it to turn a crank and raise a bucket out of a well, you have to set it up so that the current, whatever part of this rectangle is up top, the current is always going into the board here. And whatever part of the rectangle is down at the bottom, it's going out of the board. Now, after this thing turns 180 degrees, see it would switch if you haven't done anything clever. Now, there's a way around that, which people figured out pretty quickly, and that is that you can actually hook these leads up to the battery in such a way that they have little metal brushes on them, and they're brushing against the fixed contacts to your battery, so that when this thing turns around, it contacts the other side of the battery. So it's called a sliding contact on the battery. And so by being clever like this, you can always set it up so that, say, the current up top is always into the board and the current on the bottom is always out of the board. Because when this thing flips, say, the way I've drawn it, the top contact here is in contact with this part of the battery, right? Okay, but once it flips around, it'll be in contact with this other terminal of the battery. So that kind of sliding contact can be used to always make sure that the forces are in the same direction, so the thing always just spins in the same direction. Okay, so that was in the 1820s that people first figured out how to make a simple electric motor like this. Now, it wasn't practical yet, and people would have to come up with better and better designs to make electrical motors useful. But you get the principle here, and how you can turn electricity into motion and make it do work for you. Okay. So we've come a long way from rubbing pieces of amber. Now, there was something else that both Faraday and Ampere figured out that they could do with these discoveries. And that is, for the first time, people had a way of actually measuring electric current. Remember that Ampere figured out that the force between his wires was directly proportional to the current. Okay, so these forces that we're talking about here are directly proportional to the current. If you double the current, you double the force. So if you can set up a situation where you can, in effect, measure the force, then you have a way of knowing exactly how much current you have, because they're just directly proportional. So both Faraday and Ampere figured out how to make a device that would exactly respond to how much current you had in a certain situation. Yes?
Did they work on this together?
No, they actually developed it independently. Yeah, basically the same sort of setup. And I'm going to give you an example of one way you can do it. And this is called Ampere, I think, is the one that actually named this. He called it a galvanometer, in tribute to Luigi Galvani, who started this whole subject by discovering electric current in frogs. Now, the basic idea behind a galvanometer is you have, let's say you have, again, a horseshoe magnet with a North Pole and a South Pole. It's hard to have any other kind of horseshoe magnet. And let's say you have, again, a rectangular loop of wire in here. Okay, and it's giving you the side view here with, let's say, the current going in on this end and out on this other end close to the North Pole. So let's say attached to this this wire, we have a some sort of needle that's just a marker. You know, it can be made of plastic, whatever. And then there's some number scale up here. Now, when I send the current through here, what's going to happen? Let's figure out the direction of the forces first. Well, what direction is the magnetic force from the, just from the magnet? Yeah, it's this way, right? It always goes from north to south. Now, so we've got a current going into the board. The magnetic force in this direction is going to kick it down, right? It's going to take this end of my rectangular loop and push it in that direction, downward. It's going to take the other end, push it up, right? Out of the board, curl your fingers in the direction of the magnetic force, and it pushes it up. Okay? So, what's going to happen? This whole rectangular loop is going to want to rotate. As it rotates, my pointer needle is going to move, right? The more current I put in, the farther it will go. Now, it'll just spin around the way I have it so far. So how do you keep it from just spinning around? Well, you do something clever. You make it move against, let's say, a spring. Let's say you have a little spring here. Now, what did Hooke tell us about springs? Does anybody remember? That's way back from last year. That when you, let's say I compress a spring by 1 inch. Okay, now I want to compress it by 2 inches. How much additional force do I need? Double. That's exactly, Daniel's right. That's what Hooke discovered about coiled springs, is that the force is directly proportional to how much you compress it. So if you want to compress it, 1 inch, you need so much force. If you want to compress it 2 inches, you need twice as much force. Okay, so it's exactly proportional to the force. So if we have this kind of a setup, then the amount of force that is, we have a way of measuring now. We've set up a situation so that the amount that this rectangle rotates is directly proportional to the force. Daniel.
Where's the battery?
Oh, I've got leads coming out here to a battery. So here now you've got a situation where if you put in, let's say, a certain amount of current, okay, it will deflect this needle, a certain amount, right? If you put in twice as amount of current, it's going to deflect it twice as much, right? Because the current is proportional to the force. So the force on this coil will go up directly proportional to the current, and that's proportional to exactly how much it will compress this spring. Okay, so you've got an instrument now that will, where this needle will deflect exactly in proportion to the amount of current that you put through your rectangular loop. Very clever. Now, Ampere and Faraday realized something else. They realized, well, if you only have one loop here, you have to put a fair amount of current through it in order to get a big enough force to really compress this spring much. Okay, so it's not a very sensitive instrument. You need a fair amount of current in order to move this needle. But what if you put lots of, what if you wind this wire around a bunch of times? Okay, so you've got lots of loops. Well, the force on each loop is a certain amount, but every single loop has that same force on it. So if you have lots of loops, then even with a small current, you can get a pretty big force that will compress this spring. So then you have a really sensitive way of measuring even small currents. Okay, very clever. So for the first time, now this makes electricity into a more quantitative science here, because now scientists can say not just that, oh, we're causing a current in this wire, but they can define a unit, say, and then say we're working with exactly 1.43 units of current. So they can start working out quantitative relationships. Yes?
What did they label the units?
Oh, actually the units were, I think for a long time, if not now, they were defined as by an Ampere type experiment that, remember I told you about the experiment where you have a wire that is on pivots, and then you have, say, another parallel wire underneath it, and if you put the currents, say, in the same direction in these two wires, then there'll be an attraction between them, and then you can hang a weight off of this end to measure the force. Well, this is the first way that they set up units of electricity was they called the unit of current the ampere, for obvious reasons, in tribute to Ampere's discoveries. And I forget exactly how they defined it, but say, if you have 1 ampere, you need, 1 ounce of weight here to balance it or something. That's actually, it was more than that, because 1 ampere is actually a pretty big current, so I'm sure you would need more weight, but, whatever. Troy?
So what's the advantage of the galvanometer over that?
You could use this. That's right. This you can actually make into a compact little instrument where all this complication that I've drawn in here is just hidden inside the instrument, and all you see is a numerical scale, and the pointer just tells you exactly how much current you have directly, rather than hanging weights. And okay. Let's see. Let me. We're getting toward the end here this morning. One other interesting invention that was made about this same time was people figured out how to make super strong magnets. Before, people would take pieces of iron and just take like permanent magnets, pieces of lodestone, and rub them in certain ways against the iron to partially magnetize the iron, right, and make that into a magnet. Well, it didn't really magnetize the iron all that efficiently, and you didn't get a very strong magnet out of it. Now, around this time, people figured out, well, we can do much better now that we understand how electricity produces magnetism. All we have to do is take a big horseshoe-shaped piece of iron. And one guy who did this actually took about an 80-pound piece of iron. Okay, so he has this big horseshoe magnet.
Who is this?
The magnet I'm going to tell you about. I mean, I think Faraday did this too, but the magnet I'm going to tell you about is by an American scientist who got interested in this subject. His name is Joseph Henry. And you can call this, let me see. Let's just call this section electromagnets. Now, what Henry's idea is, you wrap wire in coils around this iron magnet, and so you have coils of wire all around this thing. And we know that a coil of wire sets up a magnetic force just like a magnet, right? So if you put a strong current through this coil, okay, it will magnetize this piece of iron. I mean, it will create a magnetic force in the iron. Say depending on which way you send the current through, you can make this the North Pole or the South Pole, but let's say we make it the North Pole and the other one the South. Now, Henry, in his strongest magnet, he took this 80-pound horseshoe piece of iron, wrapped 9 different coils around it, and with a huge battery, sent current through all 9 of these coils to create a really strong magnetic force that would magnetize this iron really well. And after he added his coils, he had like an 85, 90-pound electromagnet here. But he found that he could pick up 2,000 pounds of iron with it. So this was the beginning of really, really strong magnets that were produced by electricity using these discoveries of Ampere and Faraday. Okay.